In today's class, I'm going to give you a few examples of the models of motion under gravity. I think most of these are things that you do come across in many of the textbooks. Therefore, I don't want to lay much emphasis on these kind of problems, but I do give about a few models for the sake of completeness. The purpose of this lecture is to how to apply those equations that we derived, say for those equations that I have already developed the other day under motion under gravity for 1D motion. Now, the first example, I'm looking at a case where a dropped body covers almost say 1/8 of the total distance during the last second of its descent. During the last second of its descent. What is the time of flight or time of descent, and what is the height? This is the question. Some of the models, I'm generalizing it. I'm not giving you that x could be 2, 3, 4, anything. But I'm just trying to give you a generalized problem model. Now, for example, let the whole time of descent here be n seconds. Then the last second is your nth second. Agreed? This is the last second, which is your nth second. Now, in nth second, what is the displacement? H by x. Sn is equal to u, which is 0, plus a by 2 into 2n minus 1. This is a direct application of that formula for displacement in any particular second, right? Now, you've got this. In a similar way, if the total descent is n, when you drop the body here, by the time it comes, the displacement is h, and this is ut 0, u0, plus half gt square. Gt is nothing but n. Now you have got two equations, h unknown, n unknown, time of descent. What is known is x. Now, if you rewrite this, and equate h as half gn square. Now you can g by 2, you cancel it out and write a quadratic equation, n square minus 2gxn plus x is equal to 0. Now you get a quadratic equation in n, therefore just directly solve it. How to? You write a direct known expression, n is equal to minus b, here, sorry, g won't be there because g by 2 got cancelled here. So you got minus b, that is 2x, plus or minus the root of b square minus 4ac by 2a. Now you simplify that. That would 2, if you take 4 common here, 2 gets cancelled. So n can be x plus a root of x square minus x, or x minus root of x square minus x. Now you get two possibilities, but in one of these two cases, if you look at that later one, you know this is always less than 1. You can try with any number, you will get that. You will always get less than 1. But in the problem, we said during the last second of the descent. That means that the time of descent must be more than 1 second. Therefore, this particular solution is not applicable here. So the answer is simply the time of descent is x plus the root of x square minus x. And once you get this, you want to get h, it is half gn square. So this is how you have to get that answer also. I hope this is clear to you now, right? So this is how you can make use of the problem of using that Sn expression in this. And sometimes, you know, they ask you several questions on the dropped bodies. Let me give you a few general expressions that you come across, particularly the ratios. Say, for example, you are dropping a body, as I said, u is equal to 0. What is the displacement during the first second? So I'll write S1. S1, how do you write? U0 and n is 1, 2n minus 1, therefore g by 2. S2, in the second, you have to be very careful about this. The first second, the displacement is this, so it will be somewhere here. And during the second, how much it will be? 2 into 2, 4 minus 1, 3. So it is 3g by 2. So if this is 1, this is 3. So similarly, if you go by S3 would be 5g by 2, S4 is 7g by 2, etc. If you take the ratio, what is it that you get? 1 is to 3 is to 5 is to 7, etc. This is only valid for the dropped body. First second, third second, and fourth second. Now, for example, if somebody asks you, in 1 second, it is half g into 1 square. In 2 seconds, it is half g into 2 square. And third second, it is half g into 3. Likewise, you go on writing it down. You get over. What is the ratio in this particular case? If you put it, g by 2 is common, as you know very well. So it is 1 square is to 2 square is to 3 square is to, etc. So 1 is to 4 is to 9. There is a clear-cut distinction between these two cases. You should understand that the previous one was that first second, second, third second, fourth second. Likewise, 1 second only was that interval. Here, first second, first 2 seconds, first 3 seconds, first 4 seconds. Likewise, I am looking at. So this is how you get the ratio for these things. Now, sometimes they ask you, what time does it take to cover the first meter? First meter, I am dropping the body. 1 meter, what time it takes? So 1 meter means, say 1 is equal to half g t square. I'll call it as t1. T1 is the time taken to cover the first meter. So this implies T1 is equal to how much? Under root 2 by g into 1. Now, suppose you are talking of the first meter. Now, this is first meter, okay? Now, the second meter is here. Now, this entire thing is 2 meters. So, first 2 meters, how much time it will take? T is equal to under root of how much? 2 into 2g by g. How much is that? Under root 4 by g. Using half gt square directly. But what is it I want to know? I want to get not for the 2 meters but the second meter. So what is the time? The total time I know, root 4 by g. How much time this will take? Root 2 by g. What is the time taken for the second meter? This minus this. Therefore I call this as T2 is under root 4 by g minus under root 2 by g. You get the point? So it's like this. Now you get the next meter. If I go, this is your third meter. Now this is first meter. second, third. So for 3 meters, how do you get the answer? For 3 meters, how much? I'll take it as t dash under root 2h by g. And for 2 meters, you already got this. So 3 meters time minus 2 meters time will give you third meter time. So I'll write T3 as under root of 9. Sorry, how much is this? 6. 2 into 3. 6 by g minus root 4 by g. Likewise, you go on getting. Now, I want to get the ratios of the times taken for a dropped body. Remember, ratios of times taken for the dropped body to cover first meter, second meter, third meter, and subsequent 1 meter intervals. Simply take whatever that is common. What is common here? Under root 2 by g is common. So, therefore, root 1 is to here 2 under root 2 by g means, so this will be, don't put so much, root 2 minus root 1 is to root 3 minus root 2 is to likewise root 4 minus root 3. I am putting in a sequential order so that you will never get a problem. This is as far as the times taken for the first, second, third, and subsequent meters is concerned. Now, how to use these ratios? I'll give you one example. Say, for example, a ball is dropped, say, from a height h. A ball is dropped from a height h, and another ball is dropped after an interval of delta t. Another one is dropped after an interval of delta t. Likewise, he is dropping the balls one after another at equal intervals of time. Now, the problem is, he will give you, by the time first ball strikes the ground, say, fifth ball is about to be dropped. So, this is the first one, this is fifth one. So, maybe you may have like this. So, this is second ball, third ball, fourth ball. At this instant, what are the positions of these balls? Say, from the ground. I mean, he is asking height of each of these balls from the ground. Now, how to make use of this ratio? Now, if you recall, I have already given you what is the ratio of displacements covered during 1 second intervals, right? And this ratio, you got it as likewise. I mean, I'm just like that. I'm putting as many as you wish you can put it. Now you look at, suppose if I take first 2 seconds, next 2 seconds, subsequent 2 seconds likewise. So how much I get? 4 is to 12 is to 20 is to 28 is to etc. So again 4 is common. What are you getting? So if you take first 2 seconds and subsequent 2 second intervals also, the ratio remains 1 is to 3 is to 5 is to 7. First 3 seconds, next 3 seconds, subsequent 3 seconds. Again you will get the same answer. Now, first half second, next half second, subsequent half second intervals. You will get the same ratio. Now, by analogy, this ratio is valid not only for successive 1 second intervals, but it is also equally valid for successive equal time intervals. The time interval must be same. So, how we make use of this? So, if I take this interval to be delta t, I want to meet, you can do these kinematics problem, in a number of ways. But what I am trying to do here is how to make use of the ratios that I have just given it to you. Now, the ratios part, if I see, now this part will be 3 parts, 5 parts, 7 parts. You got this point? 1 part, 3 parts, 5 parts, 7 parts. What are the total number of parts you have? 4, 5, 9, 16 parts. You get that? So each part corresponds to how much? H by 16. That's it. Now the answer is before you. Now from here you want to know what is the second ball's height. So how many parts is above there? 7 parts. Therefore, this part will be 7h by 16. What is the third ball's height? Third ball's height is, now this is 7 plus 5, how much? 12 parts, therefore 12h by 16. Likewise, you work out and give your answer. Now here we are not going to work out what is the time interval, etc. So H I have generalized it, they'll give say 16 meters, 32 meters, etc. Is this okay now? I want you to understand the usage or the utility of these ratios in some of these problems. Okay? Now, once you have got this point, now let me tell you. Say for example, one body is dropped, say from a height h. After say some 2 seconds, another body is dropped. Another body is dropped. So this is the first body, this is the second body. What is the time interval given? 2 seconds. Now, initial, what is the height difference between these two? If you want to know what is the height difference between these two. Simple. From this height, in 2 seconds, how far this must have come down? Half g into 2 square, that is equal to 2g. G value I am not substituting. You can, as per the value given, you can substitute 9.8 or anything, any value that they give, you can do that. Okay? So that is about this one. Now, the second body, instead of, suppose when I am dropping this, the initial difference that you have seen, that is 2g. Obviously, it will take its own time. They may ask you, after 2 seconds from the time the second body is dropped, what is the difference in the heights of the two bodies? How do you give answer to that? Very simple. 2 seconds after the second body is dropped. That means first body has gone by how much? 4 seconds. So what is the displacement in 4 seconds? Half g into 4 square. And in 2 seconds, how far this will come? Half g into 2 square. So you can simplify and give answer to them. Questions could be of this nature. That is number one. Now, at one stage, if you see, this goes on increasing, that wide apart, till the first body touches the ground. Afterwards, that difference in height goes on decreasing, and becomes 0. This is one model. The other model is, first body is dropped, after 2 seconds, second body is thrown down with a velocity u. Now, many questions they'll ask, when and where do they meet? When and where do they meet? Suppose I am taking a point from this height, say at a distance x, let me presume that they meet. Now, if I take, say, first body and this is second body, what is initial velocity of the first body? 0. Initial velocity is u. And suppose the displacements of both the bodies is xy, because this body is dropped from the same point. That's number one. Number two, suppose the first body takes time. Now remember, here many of the students get confused whenever you are writing in this fashion. Now, what time this second body will take? Will it take t minus 2 or will it take t plus 2? So when you do work out these problems in the exam, you always tend to get this confusion. So always keep in mind which body is actually traveling for a long time. Obviously, first body. So the time of the first body should always be more than that of the second body. Therefore, it should be t minus 2. But remember, this time, if he asks from the moment the second body is dropped, you better take t here and write t plus 2 here, okay? And then, so your equations are given. Use the general standard equations. If I write for this, x is equal to half gt square. And if I write here, x is equal to u t plus half g into t minus 2 whole square. Now take these two equations, because these two are same. So you get half gt, that is u into t minus 2 plus half g into t square minus 4t plus 4. In this, of course, half gt square gets cancelled, and now you have 0 is equal to ut minus 2u, and this becomes minus 2gt, and this becomes plus 2g. Now what are you getting here? T into u minus 2g. Now this and this, I'll bring it on to this side, so I can write it as 2 into u minus g. Now what is the time taken? That is how you solve this problem. Although I've gone down a bit too below, solving is not a big deal for you. You can very easily solve this. I'm writing this expression here for your convenience. So this is your answer. When and where do they meet? So first you have given time, and if you want to know what is the displacement, you simply give it as half gt square. I hope you have understood this point. And this is one model. They generally ask. And there are, in kinematics, there is no depth of models and problems. You keep on working on as many as you wish. The biggest problem is if you think that I have done 100 or 1,000 problems, in the exam you will get 1,001st problem. So the best option for you is to learn the concept of how to attack the problem, and accordingly you work out that problem at that instant of time. But if you have that practice, you can do it rather quickly. All right. Now you see another model that I give you. Here is a body dropped simultaneously along the same line. Another body is projected up with you. So body dropped from a height h, it is projected up with you. As usual, when and where do they meet? It's a simple question. In the previous case, I took both the bodies to be in the same direction. One is dropped, the other one is dropped, the other one is projected down. Now here, simultaneously, this body is projected up, this is dropped here. When and where do they meet? Now, how do you work out this when and where do they meet? So, what do you do? Let me, as usual, let the displacement of that dropped body be x. Therefore, the displacement of this is bound to be h minus x. Now, in the first case, let it take a time t, therefore this will also take a time t. How do I write equation for this? H minus x is equal to ut minus half gt square. S is equal to ut plus half at square formula. And this is a dropped body, g downwards, x downwards. X is equal to half gt square. And we solve this. So this will get cancelled, this will get cancelled. H is equal to, now people say T is equal to H by U. Now there are certain models in kinematics where you can't get carried away with the answers that you have. You have to be very careful of what answer are you giving. And although technically, theoretically this is right, in reality this may not be the right answer. I'll give you an example of when this is not possible. Okay? Now you just look at that. Incidentally, by this time, what is the velocity of this? We will call it as body number 1. We will call it as body number 2. So how do you write that? So V1 is equal to U plus AT. V2, this is V2 is equal to U minus GT. Now if I add these two, now this is another important result. The final velocity is, the magnitudes of the sum is always equal to sum of the magnitudes of the initial magnitudes of velocities. One point which you can always keep in mind. Now coming back to our problem in this, if I take a practical example of 100 meter height, I am dropping this body. What is the time of descent for this? Under root 2 h by g. Dropping body, you look at the time of flight expression, u becomes 0, that will leave you with only under root 2h by g. That's what I'm using it here. So root 20 approximately 4.5 seconds, approximately. Suppose I am projecting a body up with 10 meter per second. What is the time of flight of this body? To go up and come down, to go up and come down from the ground. I already gave you the expression. From the ground means h is equal to 0. So you get u by g plus u by g, 2u by g. So it is 2u by g, or I am taking for the time being 2 seconds is the time of flight of this body. You can very clearly see. You see, h by u, you say, is the time in which they will meet. Where have they met? They have not met anywhere. The body has come back, and after the 2 seconds, another 2.5 seconds, you wait, then this body will reach the ground. But your theoretical answer is h by u. Therefore, now this is where, see, school level, we definitely give this kind of answers. There's nothing wrong with that. But now, every time you give an answer, you have to be very careful. Your time and work, if you recall, a work can be done by 2 persons in 2 days. The same work can be done by, say, 4 people in how many days? So your tendency is for 2 people 2 days, 4 people 4 days. Now this is how you are tempted to give the answer. You know that it is wrong. So in a similar way here it is not wrong, but theoretically this is correct, but practically this is not tenable. Now, if that is the case, what is the condition for the, first of all, these bodies meet only on the ground. Now I want to now get for such a model, my first condition is, what is the condition for the bodies to collide above the ground? Be careful now, the way we discuss the problems will be definitely different compared to what you have already learned in your school days. That's what I want you to be careful. I'm now looking at a condition where these two would definitely collide above the ground. That means what? How to put that condition? Now you have to think for a while. I'm dropping this body here, right? And this is going up somewhere. Now I want this body to definitely collide. What do you mean? What is the time of meeting h by u? If h by u, let us say, is 2 seconds, that means this body to go up and come down, it should not come down before 2 seconds. You get my point? If 2 seconds is the time they made, and I don't want this body to go up and come back in 1 second, then these two cannot wait. So for the bodies to definitely wait, what is the condition? This time of flight here, this must be more than the time for them to meet. So the time of flight to u by g must be greater than or just equal to, at the most, this is a border case, remember. And this is t equal to h by u. Therefore, you have u square must be greater than or equal to 2u by g is equal to h by u, right? Or you can write it as u square must be greater than or equal to gh by 2, or u must be greater than or equal to under root gh by 2 is the first condition. If this condition is satisfied, then the bodies would definitely collide above the ground. Okay? That is a first condition that we have. But if I can visualize a scenario where the body dropped is coming and this body dropped is ascending state. It is still ascending, but I want these two to collide. One is descending, the other is ascending. Right? What is the condition for the bodies to collide while one descends and the other ascends? That is the condition. What is condition 2? Ascent and descent. This must be ascending, this must be descending if you want it to definitely collide. As usual, what is the time for collision h by u? Suppose, as I said, suppose h by u is 4 seconds in an example. Your time of ascent must have more than 4 seconds. Then it still keeps on rising or ascending. Therefore, time of ascent, you know very well, is u by g is greater than or equal to h by u. But equal to no, when you say ascend and descent, it should be like this only. Therefore, u must be greater than gh. This is the second condition. If u is exactly equal to root gh, this body will come to a stop momentarily and this body will hit it. Likewise, it will happen. Now my question is, third condition. What is the third condition? I want these two bodies to collide while both of them descend. Both of them descend. How do you give that answer? How do you give that answer? Yeah. Think for a while. I want both of them to descend. If I take this, you can't give guarantee. And this should not be the case, but this should be the case. You get my point? That means what? U must be less than under root g. But u must be greater than under root gh by 2. I hope you have understood. It's a very, very important concept. I want you to understand. Never just like that, never give answer. It should be less than root gh. That will not solve the problem. It should not only be less than root gh, but it should be also at the same time more than under root gh by 2. Then only this is possible. You understood now? So when such kind of problems are given, do not blindly give your answers and try to work out whether this is satisfied. And if it is satisfied, then yes, what you got then is right. Then you can give such an answer. I hope this model also is clear to you. There are many cases that will be coming across in many of these books, as I told you. There is no depth of any such models in the book. You can follow. I'm sure with the knowledge that I have already given it to you, you'll be able to solve most of these problems, if not all, okay? Now, I'll slightly deviate from this. You are talking of, let us say, a body projected up, reaching the maximum height. We will call it as h. And the time of ascent is u by g, if I project it with you. Now all this is in a vacuum case. Air is absent, or in other words, the drag due to air is absent. There is no resistance offered by the air. Then this is valid. Okay. And now what about if this body goes up and then comes down? So you know that h is equal to u square by 2g. And if this body starts its descent, what is the time of descent? Under root 2h by g. But if I substitute this h, 2 by g into h means u square by 2g. This is equal to u by g. So time of ascent is equal to time of descent in this case. Remember, this is the many books give this as a universal statement. That's not correct. It should be to the same point of projection or level of projection. Then only this is valid in the absence of air resistance. Now, for example, I presume very crudely, if I presume that the air does indeed offer resistance. If that is the case, if I project a body up, you know that the acceleration due to gravity is downwards. And you know one important thing is, when resistance is offered by any medium, any fluid such as air or water, it's always against the velocity of the body. And velocity of the body is upward now, therefore resistance must be downwards. So I want to take the resistance acceleration as A. So what is the effective retardation or effective acceleration that this body is subject to during ascent? The effective acceleration will be A effective is G plus A. So what will be your time of ascent? Time of ascent, I'll write it here. Time of ascent is U by G plus A. That is one point which you should understand. Right? Now, what is H? U square by 2 into G plus A. This is during the ascent. Oh, got? Now, with this background, you can find out what is time of descent under root of 2h by. Now, descent, what happens? This is the velocity direction. Therefore, this is A and this is G. Now, resistance is upward. Acceleration due to gravity is downward. Therefore, the effective acceleration here is G minus A. Never write A minus G. The body will never come down. Remember that. So, under root of G. Now, what is H? Substitute it here, as I have done in my previous example here. H, how do you write? U square by 2 into G plus A, that is equal to U by, this is time of descent. You can see time of descent is not equal to time of ascent. If I compare and then try to compare these things, if I compare, what do I get? We will take the ratio. What is TA upon TD? U by G plus A, right? And this is U by root of g square minus a square. So u gets cancelled. Now this will give rise to g minus a by g plus a, which is always less than 1, because numerator is less, denominator is more. Therefore, very simply you can give time of ascent is less than time of descent. Now this is a very important conclusion. Whenever a resistance is taken into account, although we can't give the precise values of ascent and descent separately, your time of ascent is less than time of descent. And if somebody asks you what is that ratio, probably you will have to go with this and give it as under root of g minus a by g plus a, but not g minus a by g plus a. Many people write u by g minus a, u by g plus a, and that is absolutely wrong. This is the correct option for this problem. So this is one out of the way example when you consider the comparison of time of ascent and time of descent. I'll put a stop to this lecture here. In my next lecture, I will